Hello everyone, I'm Liu Pan, the Chief Product Officer at D2S. Today I'd like to give you a highlight of a review paper I did for SPIE called Inverse Lithography Technology, ILT, 30 years from concept to practical full chip reality. Why we want to talk about ILT? Because ILT is the most computational achievement in the whole semiconductor manufacturing. What you see here on the left, this is the Curvilinear ILT mask pattern. And on the right, those are the pictures of the simulated wafer image. And in my talk, you are going to see a bunch of those movies. They are actually a sequence of different configurations. I put them together so that you can see the continuity and also you can easily tell the symmetry of the solution. And you can view it very quickly. Okay, let's begin. When we talk about ILT, we need to mention OPC because the OPC is the first attempt to make the wafer print by computing the mask patterns. It is edge-based, started from a rule-based approach by adding the serif to the contact, and later on model-based, and those modifications are more complex and also added scanning bars. But ILT is different. ILT in general is a pixel-based, and it's a iterative optimization, so the runtime takes much longer. It's at least the order of magnitude longer than OPC, and sometimes it's actually 2 orders of magnitude longer than OPC. The research for ILT started in 1990s. People tried all kinds of different methods, simulated annealing by flipping pixels. The first attempt to commercialize ILT product came from Luminescent. I was a co-founding member of Luminescent, and I coined this name, Inverse Lithography Technology, ILT. In 2005, at Bacchus, we have 5 partners presented their ILT result. Then in 2006, at SPIE, our CTO Dan Abrams and I presented this paper called Fast Inverse Lithography Technology. This is considered as a milestone of an ILT paper. It's the most quoted ILT paper as well. You look at those pictures, you see those curvilinear mask patterns, and also you see we are trying to simplify it so that it can be written by VSB mask writer. So what is ILT? ILT is a technique to treat the mask optimization as an inverse problem. As you see, we can actually model the scanner optics very well. So starting from a mask pattern, we can run a litho simulation to simulate the wafer pattern. This is called the forward function or forward simulation. But what we want to achieve is based on a pattern that the designer want to print on wafer, we'd like to calculate the mask patterns. Mathematically, this is like solving the inverse problem. That's why I called it inverse lithography technology. Most of the ILT are actually iterative optimization. Here I use the D2S result as an example, but you can see this in other approaches as well. So started on the left, this is the mask pattern. Then doing the optimization, you are seeing we show the cost function and the gradient of the cost function. You see, doing the optimization, those sRAFs are generated. And also when you look at the wafer contour, you see the wafer contour is approaching the target. At the end, it's pretty much overlapping with the target. And also you look at the cost function and the gradient of cost function, they approach to 0. There are many ILT papers with all kinds of different approaches, but there are 3 companies, they have published papers showing their full chip ILT result. The first one, Luminescent. Luminescent came up a very smart method to solve this problem. This came from Luminescent's co-founder, Professor Stan Osher, a very famous mathematician who invented level set method. As you can imagine, when we solve the ILT problem, we need to come up with those assist features. But when you look at it in two-dimensional, when there is assist features appear, the topology changes. Mathematically, this is a very hard problem to solve. Level set method is a way to solve this. The idea is in two-dimensional, there are discontinuities in topology, but if you create a mathematical function called distance function, basically it's the distance from this point to the edge, then this becomes a three-dimensional smooth function, like a peak and valleys. And you can imagine something popped up and across the, I would say, the sea level, which is a zero level site, then that would be a new feature and could be a cis feature. So this solves the discontinuity problem in topology. Intel has a totally different approach. They call theirs pixelated mask. They are trying to use a chromeless mask. So this is a glass and just etched in the different depths. The idea is to use a strong interference to improve the resolution. There are quite challenges because those pixels, they are fairly small, so you need to consider the mask 3D effect. So they developed the mask 3D model for that. And also it's really challenging for inspection. As you can imagine, you do a high resolution mask plane inspection, you just see a transparent glass. That's why they have to work with applied materials to use error image mask inspection to solve this problem. The third approach was invented by Gouda. They started as a GPU-accelerated OPC startup. Then later on, they came up their own method to solve the inverse problem. And what's really unique is not only is the GPU accelerated, but also they are trying to solve the problem in frequency domain. Because the scanner optics is band limited, solving the inverse problem in frequency domain is band limited. There's some benefit in terms of symmetry MRC I'm going to show you later. And Gouda was acquired by D2S, so the D2S approach was based on Gouda's pattern. There are numerous papers, especially from Luminescent, working with their partners and the customers, showing curvilinear ILT give you the best result in terms of process window. So this is one given by BJ Kim at Samsung. They worked with Luminescent. It shows this is a compact array, and the pitch changes from dense all the way to isolated. Luminescent generated those different flavor of ILT patterns from something really simplified like OPC scattering bars all the way to the ideal curvilinear ILT patterns. And it shows for every pitch, the full curvilinear ILT mask pattern gives the largest depth focus. Not every curvilinear ILT gives you the same result. Actually, the real domain solver, although it gives you the curvilinear pattern, but you may end up some patterns are too small, it violate the mask rules, or they may have sharp corners. The band-limited frequency solver, like D2S did, since the optics is band-limited and they're solving this in frequency domain, therefore it's guaranteed it doesn't generate those sharp corners or really small patterns that violate the MRC rules. And also another benefit is solving it in the frequency domain, you tend to get symmetric patterns when the original pattern is symmetric and not the source is symmetric. I'm going to show you some examples. So to today, ILT has been used by pretty much all leading semiconductor manufacturing companies. They all treat this as one of the core lithography technologies. This is the result from eBeam Initiative survey. It shows ILT has been used in the critical layers, but not in every critical layers. And most of them, they have been used in hotspot for the small area. So why is that? Why just don't use a full chip curvilinear ILT everywhere? Well, it turned out there are two technical challenges. The first one is a mask writing. The mainstream mask writer is called a VSD mask writer. It basically writes a single shot with a different size. It's like a rectangle or as a brick. So if it is a Manhattan pattern, you can use this different size brick to kind of like build your pattern. So it's very fast for Manhattan pattern. But when you want to write a curvilinear pattern, use VSB mask writer, then you have to use very tiny, small breaks. Then the result is you have too many shots. Since the write time is proportional to the number of shots, therefore the write time is too long. It's not practical, because the practical write time is about like 1 day, and this may take quite a few days. So it's not practical. Fortunately, the photomask industry recognized that challenge. Both IMS and the New Flare started the development of a multi-beam mask writer. In the multi-beam mask writer, it has a head. You can actually write about 260,000 beams all together at the same time. And you can turn on and off of each beam and also change the exposure time. So you can write those pixels even in grayscale. So the write time is constant no matter what kind of pattern you want to print. And they can write the entire mask roughly in about 12 hours, and some maybe up to 24 hours. So this solved the bottleneck of mask writing for curvilinear mask patterns. And it turned out using curvilinear mask pattern has a whole bunch of benefit other than just the ILT itself. Dr. Ryan Perman from D2S, he showed just to print the contact, if you change from a square shape to a curvilinear circular shape, and also change from a VSB mask writer to multi-beam mask writer, you can reduce the wafer variability by 75%. That's very significant. The second bottleneck to do full chip curvilinear ILT is actually the ILT program itself. Just to think about it, the full chip OPC for the leading edge, it would take like tens of thousands of CPU cores and run a few days. ILT, as I said, it actually order or 2 orders magnitude higher. That's because first step, you have to calculate this curvilinear full chip ILT solution. In order to get a full chip ILT solution, especially for VSB mask writer, there are so many extra steps you have to run. First, you have to split the full chip into those small areas we call partition. Then you give each partition to a CPU core to calculate. And you first calculate the curvilinear solution, but then you have to do we call Manhattanization, so that you can generate a pattern that VSB mask writer can write. And then, since the pattern is changed, you have to redo the optimization. And after that, when you put those together, you found a big problem that's called stitching issues, because the sRAF generated from the left partition may not be consistent from the sRAF from the right partition. And those problems were eventually solved by D2S. So the D2S solution is kind of like unique. As I mentioned before, it's a band-limited frequency solver, and it's a GPU accelerated. But on top of that, we came up a new method to solve the stitching issue. First, let's talk about the GPU. Why we want to use a GPU? Because GPU can accelerate those computations. The reason is that GPU is a single instruction, multiple data, while CPU is a single instruction, single data. So GPU has massive parallelization. Although CPU has multiple cores, we're talking about the tens of cores, but on GPU, we're talking about like thousands of cores. Turned out many calculations needed in computational lithography can be greatly accelerated by GPU. For example, Gaussian convolution, convolute with all kinds of kernels, and also the FFT. For those operations, GPU can accelerate it over 100 times. So GPU is good for ILT. Then how to solve the stitching issue? As you can imagine, a GPU is doing the parallelization, and we can solve certain area. So if you can imagine you have a virtual gigantic GPU, then the area is so large that will cover the full chip. So that's the basic idea that D2S came up to solve the stitching issue. As you can see in this example on the left, this is the ILT solution using the conventional partition by partition approach, very similar to OPC. Then you see that there are 6 features from the left partition, but if you look at on the right side, you don't see that 6 features. So it causes this stitching issue. And the way to solve the stitching issue, you have to take the whole area, close the boundary, and rerun the calculation. But it won't guarantee you will solve the problem because you create new partition boundaries. So the problem never ends. But then if you look at those results from a D2S stitchless approach, then you see the SRFs are all continuous across the stitching boundary, and even those main features, they are very smooth across the stitching boundary. And this approach cannot be done by just the software. We need to do a software and hardware co-optimization. Although we use off-the-shelf GPUs, but we have to design the whole system so that it can actually solve this full chip curvilinear ILT problem. And we call those platform CDP, Computational Design Platform. So far, we have shipped over 40 CDPs worldwide. They are pretty much in every leading mask shop and some wafer fabs. And most of them has been used together with NeoFlare's mask writer to do some real-time corrections for the mask writer. Now let's talk about production ILT, what is required. There are many requirements from wafer fabs. For example, the runtime has to be fast, has to be either 1 day or a couple days, and no stitching errors for sure. The mask has to be resilient, and also you can meet the EPE requirement. So this is not just the SRF generation, it can replace the entire OPC. And also they care about the symmetry. If the original pattern is asymmetric, the solution better to be symmetric. And also has to be MRC clean, meeting the mask rules. So here I use a D2S solution to show you what those means. First, let's look at whether the solution is continuous and symmetric. So here we have a 3 contact. We change the pitch of those 3 contacts. They are symmetric configurations. As you see, when the pitch gradually increase, the ILT solution, they are symmetric and they are continuous. The second example, we use this array. And here we not only change the pitch, but also we rotate them. So this is a very challenge. But you can see this D2S solution, they are continuous and they are symmetric all around. And also you have to meet an MRC requirement. Although you generate curvilinear ILT mask patterns, it doesn't guarantee you always meet the mask rules. So those are like minimum area, minimum CD, minimum space. So you need to have a mechanism to clean up, to make sure your patterns satisfy the mask rules. And it turned out the mask rules in curvilinear space is actually simpler than in Manhattan space. For example, you have a minimum curvature, you can imagine there is a ball you can roll around. If you can smoothly roll them around, then they satisfy the minimum curvature rules. But if they stuck there, that means there's a minimum curvature violations. And you can do this outside as well, so you can use this to check the minimum space rules. Okay, we have been talking about the ILT algorithm for a while, but the main benefit for ILT is a wafer print. So here, let's see. So this is a wafer result we got from Micron. The mask was written by NeoFlare multi-beam mask writer, then it's printed using Micron's POR process. On the left, this is a ILT mask pattern, that whole sequence for this 11 by 11 contact with rotations. And on the right is a corresponding wafer print. We have to compare with OPC because we want to show the benefit of doing ILT. And here, the same pattern was treated by OPC and also treated by our ILT. We printed them and also vary the process conditions. And those every pair is at the same condition. Now you can tell definitely ILT print those wafer much better than OPC. Some of the OPC patterns don't even print, some printed really poorly. And then we measured the process window. This we use another layer, a cut layer, and we printed at a different focus, printed at different exposure. We use a 10% CD change as a spec for process window. And here, all of the print that within that process window, we highlighted in green. As you can tell, the green box using ILT is pretty much more than doubled what OPC got. And here are the CD measurement, and also we show the 3 pictures at the nominal condition, at the 60 nanometer defocus, and the 60 nanometer defocus at a 93% dose. And clearly you see ILT printed much better than OPC. Okay, that's the end of the story for curvilinear full chip ILT using multi-beam mask writer. But still, the mainstream mask writer for most of the mask house are still VSB mask writer. Is there a hope to do actually full chip curvilinear ILT even using VSB mask writer? Well, many people tried that before, started from Luminescent, trying to align those edges so that it will reduce the number of shots. But the most significant invention actually came from D2S. It's called the overlapping shot. The idea is to allow the shot to overlap, and by doing this, you can actually reduce the number of shots. And also another benefit is those overlapping area has a higher dose margin, so the slope is steeper. That will give you higher pattern fidelity as well. But once we have the full chip curvilinear ILT product, we came up with another idea. The idea is instead of try to use those shots to match the curvilinear mask pattern, we can actually try to match the wafer pattern. To do that, we can first do a mask simulation, then based on that to do a wafer simulation. So we optimize the shot based on both mask and wafer. That's why we call this the mask wafer co-optimization. Before I get into the detail, I just want to show you what's the flow at the mask shop today. So you gave the OPC shop the target, they run OPC, they give you those polygons, post-OPC mask patterns. And you give those patterns to the mask shop, and they will do bias, they call MPC, then they also break this into VSB shot. Therefore, they call that fracture. But in this new flow, we have to change that a little bit. The OPC shop will directly generate those shots. Then they give to the mask shop, then they only have to do a little bit bias, and it's ready to print. Here, I like to correct people's wrong impression on masks. Although some of the OPC patterns are Manhattan, but when you print it on mask, those patterns tend to be curvilinear. That's because E-beam have some kind of blur effect and also resist that as well. So you have those overlapping shots, then you look at the simulated mask pattern, they are actually curved. Then the next thing is to reduce the number of shots. It turned out 80% of the shots come from SRAFs. That makes sense. For contact, there are many SRAFs. So if we can significantly reduce the shot count on SRAF by using overlapping shot, then keep the main pattern still using conventional shot, we can get the job done. Here is an example of MWCO. First, this is a before MWCO. It generates a shot, we run a mask simulation, we run a wafer simulation, and it turned out we are about 2 nanometers off from the wafer target. In MWCO, we don't have to dramatically change the shot configuration. We just have to move them slightly, then do the mask simulation and do the wafer simulation. Here we can see that 2 nanometer gap on wafer becomes 0. So that's the trick. It turned out this MWCO can significantly reduce the shot count. So here is an example for this whole sequence. And the left is conventional. So you see if we use an overlapping shot, we reduce the shot count by roughly 50%. Then if we use MWCO, we can reduce the shot count by another 50%. MWCO's total shot count is roughly about the same as OPC. Here are the real masks made by Micron. You see the left is a conventional, the middle is an overlapping shot, and the right is a MWCO. And here you still see the entire sequence. So remember this is 11 by 11 contact, we are changing the pitch, we are changing the rotations. And you do see for some of the configurations, those SRAF are greatly simplified to a single shot, and some of those just a couple shot. As you recall, the write time for VSB mask writer depends on the number of shots. So it turned out if you control the shot density below certain level, the VSB mask writer can write it faster than multi-beam mask writer, which is 12 hours. And this magic number is 36 shots per square micron. And here we look at the entire sequence. Remember that 91 configurations for this contact array. It turned out for every configuration, we can control the shot density below that number. What that means? That means you can write an entire curvilinear ILT mask using VSB mask writer under 12 hours. We also have to look at the process window. So here we look at the 61 different sites and plot the process window. Basically, the green area means within the process window. So compare OPC to overlapping shot to MWCO. You can see overlapping shot and MWCO improve the process window by over 2x, which is very significant. So here are the real mask and the wafer print. Still that sequence, you can see the entire sequence of the contact were printed very nicely, no matter they are at the center or they are at the edge, no matter what kind of pitch, because some of the pitch we do have SRAFs. All right, so far all the result I showed you for 193i immersion. But ILT actually can be extended for EUV. Actually, when ILT is required by EUV, which pretty much at 3 nanometer or 2 nanometer, you do need ILT because at that node, you don't have a high-NA EUV scanner and you have to do multiple patterning. So ILT is very critical, especially those curvilinear ILT. My ex-colleague Tom Cecil at Synopsys, he showed this result. It shows you can use curvilinear ILT to correct the asymmetry problem in EUV. Recently, deep learning becomes a really hot topic. People are trying to do everything using deep learning. So deep learning can definitely help ILT, for example, to improve the model used in ILT, like mask 3D model, NTD model. But ILT itself can also be accelerated. So the basic approach is you have an ILT product, you generate an ILT pattern, and you use that to train your deep learning model. Then you can generate those ILT patterns. Then you do some iterations. The first paper was presented by Brian A.S. in 2017. Later on, there are many different approaches to try to solve the problem. I also presented a paper to show our deep learning-based ILT that can generate those ILT digital twins. And we believe those digital twins are perfect for companies like doing inspection or repair. They can use the ILT digital twin to generate curvilinear ILT patterns to run through their inspection or repair. There are also a very interesting paper I'd like to mention by Dr. Peng Liu. He showed that you don't need an ILT program. You can use enforced learning to generate an ILT pattern directly, which is very interesting. Since the ILT is an iterative optimization and the deep learning is basically pattern matching, so in general, the iterative optimization cannot be totally solved by pattern matching. Therefore, I believe deep learning can greatly improve the speed of ILT, but whether deep learning-based ILT can replace the ILT program itself, I still doubt it. All right, that's the end of my talk. I hope you like it. If you want to learn more, you can read my review paper. I also want to mention my ex-colleague at Luminescent, Dr. Danping Peng. He is going to give an invited talk at SPIE Advanced Lithography in spring. He is going to talk about the ILT in high volume production. So we are really looking forward to that. Thank you for your attention.